All these right. There we go. Okay, so it's about time to get going. Let me welcome everyone to, I think this will actually be our final seminar of the summer. And we're very fortunate to have Waddy Taylor from MIT here. And Waddy has kindly agreed to give us a big picture overview of F-theory in the string landscape. All set.
Great, thanks a lot, Sav. So let me just share my screen here. As I was saying to Sav, I'm going to try a slightly new technical board software, which hopefully will work smoothly. Everybody can see you can see, Sav, the screen again?
Yeah, the screen is coming up.
Sav, you can, okay, great, perfect. Okay, so yeah, thanks a lot for having me there. Several changes in timing, but thanks very much for people who have managed to show up and have figured out when this is happening. So today, as Sav said, he had requested for me to give kind of a big picture of what we know about the string landscape from F-theory. And this kind of is a thread that I and various collaborators and lots of other people have been working on for like the last 10 years. So what I'm going to be talking about today is kind of a summary of some of what I think are the more interesting things that have come out of this effort. You know, I think I've got like 30 papers on things related to this, with many of these collaborators mentioned in the screen here. Let me just see. Okay, so I've got, yeah, good. So I can draw on there. So I've got lots of work on this, which I'm really just going to give kind of a big picture of. It's a little bit like if, you know, someone spends 10 years in an exotic continent like Australia or Africa, and they come back and sort of try to give you the highlights of that. I'm really not going to try to dig too deeply into the details. I'm going to try to focus on some of the main lessons we've learned and understand how F-theory really gives us a global picture of many aspects of the space of string theory solutions. So I'll start by just very briefly saying a few things about F-theory. And I'm not really going to use a lot of the technical details of F-theory. So I really want to, for those of you who know F-theory, this is just a quick reminder. And for those of you who don't know F-theory, this is kind of giving you a flavor for how this tool works. It's basically a geometric encoding of physics. And then I'll talk through several different things. One is how F-theory really gives us a global picture of the space of Calabi-Yau manifolds. And that's something people have been trying to understand for a long time. And from the F-theory point of view, we get some new insights into that. That's probably the least physicsy thing I will talk about today, but it's the thing which underlies everything else. So I will spend a little time on sort of talking about how this geometry of Calabi-Yau manifolds that we can understand from F-theory, really we can get a big picture of that, which then allows us to ask specific questions like, if you look at the big picture of the string landscape, what are the typical gauge groups or typical matter that arise if you have a fixed gauge group? That's part two. Part three will be about essentially what can you get from string theory or F-theory? Are there differences between what you get from low energy physics with the constraints we know of, like anomaly cancellation, and what we can actually get in string theory? And then finally, I'll talk a bit about how we might actually get the standard model in F-theory, different ways that we can get realistic physics in F-theory. And this ties into some more recent work that I and collaborators and others have been working on. So that's kind of the outline. Again, I'm just going to start with a quick overview of how F-theory works. Basically, F-theory is a dictionary between geometric structures encoded in the language of algebraic geometry and physics of, in particular, supersymmetric string vacua. And it was developed by Morrison and Vaffa quite some time back. And over the last 15 years, it's been used increasingly as a tool for understanding both string phenomenology and big questions about the space of string backgrounds. So the basic idea of F-theory is we can think of it as a compactification of a type 2B string theory, but on a non-Calabi-Yau space. Usually, if you think of a string compactification, you start with a Calabi-Yau space. We'll talk more about what those are. That's something which would preserve supersymmetry. And in this case, we're going to compactify type 2B on a non-Calabi-Yau space, for instance, a complex projective space. If we compactify on a complex surface, that's a real 4-dimensional or complex 2-dimensional space. Right, so that's a 2D complex space, we get a 6D theory. If we compactify on a complex 3-dimensional space, we get a 4D theory. The compactification on that base can be associated with a bigger geometry, which is actually a higher dimensional space. If we have a complex base surface, then the full space X would be a Calabi-Yau threefold, or a complex three-dimensional space X, which is mapped by a fibration into the base, so that over every point in the base, here's a base here. I hope you can see my cursor as well. Here's the base. Over every point in the base, there's a fiber, which is a copy of an elliptic curve. This gives us, in general, a fibration, or an elliptic fibration. And over certain subloci in the base, the fiber degenerates. And that's how F-theory encodes all the interesting action of the physics. The gauge group and the matter are encoded in singularities in this elliptic fibration. So since here we have complex codimension 1 thing on the base, which supports, in the language of type 2b physics, a 7-brane, and that carries some gauge group. And at the intersections between the branes, or more generally at codimension 2 loci, we have matter arising. And in some cases, we can think of this in terms of perturbative string theory, just like open strings ending on 7 branes, or at the intersections between 7 branes. But part of the power of F-theory is that it's really non-perturbative and allows us to describe things like exceptional groups and things like that. So an F-theory model is defined by...
Waddy, it's a little hard to see your yellow.
Great. Let me change to a different color. Is that clearer? Red.
Draw something.
I'm just circling some things. Okay, so this is defined by a Weierstrass model. You getting that?
Yes.
Great. Yeah, there might be a little lag between when I draw and when it appears on your screen.
There's a little lag, but the red is quite visible.
Okay, great. I'll stick with the red. That's probably clearer. So basically, an F-theory compactification is defined by what's called a Weierstrass model, which is just an algebraic way of encoding a elliptic curve over every point on the base. So what we want to do is to try to get a big picture of the set of F-theory models, which means we want to basically classify all the elliptic Calabi-Yau threefolds and fourfolds for 6D and 4D F-theory constructions. And the general approach we can take to doing this is, first we try to classify the bases. Sometimes the choice of base will force us already to have some gauge group, and we'll talk more about that. Once we've classified the bases, we can then tune some additional gauge group by refining the choice of Weierstrass model. And then we can go even further. We generally start with generic matter. We'll talk more about that and get to some exotic matter. So once we classify this set of models, we can address these 4 questions I was talking about. What can we learn about Calabi-Yaus? What gauge groups and matter are generic or fine-tuned? What theories are allowed in this geometric construction versus not allowed? And how can we get standard 4D physics? So let me just talk a little bit about Calabi-Yau threefolds. So these are manifolds which have been used through the whole history of string theory to compactify string theory to lower dimensions. They are Ricci flat. So basically these are manifolds on which you have a solution of the vacuum Einstein equations. And they have a complex structure which gives them a Kähler structure from the mathematical point of view. And from the physics point of view, this is compatible with supersymmetry. Technically, this is thought of in the mathematics perspective as having a trivial canonical class. We can think of the canonical class as like the characteristic class in some sense associated with total curvature. So these things have been studied by mathematicians and physicists for the last 30 years. They're used in the compactification of string theory. But there's still an open question, which is, are there a finite number of topological types, even of Calabi-Yau threefolds, let alone fourfolds? And I'm going to give what I think is pretty strong evidence that the answer to that is yes, and you can tell me whether you are sympathetic to that at the end of the talk. Although we don't have a complete classification, there are very large classes that have been constructed. They're the so-called complete intersection Calabi-Yaus. The biggest set is the set of toric hypersurface Calabi-Yaus. So using toric geometry, you construct a toric variety, look at a hypersurface, and there's almost 500 million polytope constructions of this. There are also generalized CCs and then elliptic Calabi-Yaus, which I'll talk about today. Okay, so the first statement I want to make is that it turns out that almost all known Calabi-Yau threefolds are actually elliptic. Now, as I say, we don't know that there are a finite number of topological types of Calabi-Yau threefolds, But we do know that there are a finite number of topological types of elliptic Calabi-Yau threefolds. So if this statement is really true, if it's true that most Calabi-Yau threefolds are elliptic without the known, then in fact we would have a proof that there's a finite number of Calabi-Yaus because we know there are a finite number of elliptic ones. So what I'm going to give you today is just a quick summary of some empirical results, which come from work that we did with my former student Yu-Chan Huang. There's also some nice work by Anderson, Gao, Gray, and Lee on the CC constructions, also showing that almost all of those are elliptic. But let me just quote one result, which is if we look at the 400 million Calabi-Yaus coming from the Kreutzer-Skarka construction, all but about 30,000 of them admit an obvious elliptic fibration in some phase. These things can have many different flop phases, and I'm actually just saying that there's a flop phase where they're elliptic. So there's a little technical issue there, but basically almost all of them have a phase where they're elliptic. So this is a picture, the famous Hodge shield of the Hodge numbers of the 470 million Calabi-Yau threefolds in the Kreutzer-Skarka dictionary. And the ones in gray, most of these, admit an elliptic fibration in some phase. The red ones are the 30,000 which don't admit an obvious elliptic fibration. Many of those probably still do, but not all. There are also some theoretical arguments for why this actually is something we should have expected. And in fact, why we expect that almost every Calabi-Yau should be elliptic. And I can go into that if there's questions at the end, but it would take me a bit far afield. So basically, there's evidence that almost all the Calabi-Yaus we know of are elliptic, and there's a good reason to think that most Calabi-Yaus should be elliptic. So that's great, but we can go further than that, and we can actually draw essentially a big picture of how all these Calabi-Yaus fit together. There are a finite number of topological types of elliptic Calabi-Yau threefolds, and combining insights from mathematics and physics, we can basically just systematically construct and almost make a list of all these elliptic Calabi-Yau threefolds. So just outlining how that works, it was shown by Antonello Garassi that the allowed bases, B2, must be one of a very small set, so-called minimal models. And for each of those, there's a finite number of different topological types of Weierstrass models. So basically, we just construct all the bases by an iterative process of blowing up these minimal bases. We can then tune Weierstrass models. We can tune non-abelian gauge groups in a way that we understand very well for the most part. Abelian gauge groups are a bit more subtle, and one can give, there are many talks that have been given on this. Paul, who's in the audience, has done some interesting work on matter and U1s. We know how to construct U1 theories with up to 2 U1 factors, and when it gets higher, it's related to some very non-trivial mathematics of the elliptic fibration called the Mordell-Weil group, and it's not fully understood. We don't have a full understanding of how to get discrete gauge groups. That's an interesting area of current research. And then matter, we understand sort of generic matter. There are some slightly exotic kinds of matter that we don't understand so well. So we have a pretty big picture of how to get at most of these Calabi-Yaus, but there are some corners where we're not totally clear on how to proceed. One of the main tools that we can use in understanding how to get all these Calabi-Yaus is the fact that certain combinations, if we have a base surface, certain combinations of curves on that surface have a sufficiently negative normal bundle that they force 7 branes to pile up on them. And these are so-called non-Higgsable clusters. So for example, if we have a curve of self-intersection -3 in the base, that forces us to have an SU3 gauge group in the physics by forcing some vanishing of the Weierstrass model at those points. Here's essentially a list of the ways that happens for surfaces. If you get any combination of curves of negative self-intersection, for instance, if -m is less than -12, then there's a bad singularity outside the Kodaira classification, which is how we understand these gauge groups, and that base is not a good base to support an elliptic fibration. So that gives us kind of an upper bound on how complicated things can get, and allows us to just go ahead and systematically construct bases. So with Dave Morrison some years back, we constructed all the 60,000 toric bases that support elliptic fibrations. With Yinan Wang, we constructed all the non-toric bases, forgetting about toric geometry, above a certain Hodge number. And basically, we have a pretty systematic way of proceeding. It gives us some new Calabi-Yaus we didn't know about before. If we then do tunings, we can reproduce essentially all of those things that we showed earlier in the Kreutzer-Skarka database had elliptic fibrations. Okay, so that's a quick summary of what we know about elliptic Calabi-Yau threefolds. And again, since most known Calabi-Yau threefolds are elliptic, this gives us actually a big picture of the full space of Calabi-Yau threefolds, which basically looks like this, based on the structure of the base. Let me say a few words about, yeah, please, question, Emil?
Yeah, so is it understood, there seems to be a lot of structure in these plots.
Huge amount of structure, yes.
Yeah, so is it understood where the patterning of this sort of phase diagram comes from?
Yes, we understand it actually quite well. This point up here is the generic elliptic fibration over the Hirzebruch surface F12, which looks as a toric geometry like this. If we blow up a point, say here, we get a new toric variety that looks sort of like this, -1 plus 11. That takes us over 1 and down 29, so that gives us this point there. We can continue blowing up points on that surface in a greedy way, and we can follow the outer boundary of this. The thing that limits how much we can blow up is we're not allowed to blow up, say, a point there, because that would turn this into a -13 curve, which goes beyond the Kodaira classification. So you can actually reconstruct the outer boundary of that shield and these gaps here by understanding those things. And actually, there's some interesting work which actually Paul and I have been involved in related to understanding mirror symmetry. We understand the thing where you go +1, -29 very well, but the step where you go like that, which is sort of the mirror of that, we don't understand as well. And one day, hopefully, Paul and I will finish a paper where we talk about some things somewhat related to that, right, Paul? Does that sort of address your question, Emil?
Yeah, I think so. Thank you.
Great, sure. Okay, so let me say a little bit about 4D compactifications and Calabi-Yau fourfolds. So we can go to a 4D F-theory vacuum by compactifying on an elliptic Calabi-Yau fourfold using a complex threefold base. Again, based on the work of Gray, Haupt, Lucas, Anderson, Gao, Gray, Lee, most of the known Calabi-Yau fourfolds are also elliptic. The empirical data suggests a very similar structure. Here's a graph of the Hodge numbers of the Calabi-Yau fourfolds. The numbers are much bigger, but they follow a very similar pattern, same kind of shield. The 4D theories are significantly more subtle in the physics because the minimal model story, the analog of those Hirzebruch surfaces that Antonella told us about, it has to use something called Mori theory, which is more subtle and complex. F theory in 4 dimensions, I didn't really harp on this, but in 6 dimensions, F theory gives us pretty much a big picture of all the string vacua we know of. There are more string vacua in 4 dimensions, even with supersymmetry, that don't come from, in an obvious way, from F theory than there are in 6D. For instance, if you do heterotic on a Calabi-Yau, which is not elliptic, of which we've just argued there are not many, but the quintic is an example, that doesn't have a well-understood F theory dual. The other thing is that in 4 dimensions, in 6 dimensions, all these theories fit together into one big, beautiful moduli space, and there's essentially only one theory. In 4 dimensions, fluxes in the superpotential lift the vacuum structure so that we have these isolated pockets, kind of this discretium, and this is where the 7-brane dynamics and superpotential are not as well understood. But the evidence so far is that the moduli space of Calabi-Yau 4 geometries is very parallel to that of Calabi-Yau threefolds. Okay. Again, we can try to classify all the bases. I mentioned that with Dave Morrison, we found all 65,000 toric bases for Calabi-Yau, elliptic Calabi-Yau threefolds. If you try to do the same thing for elliptic Calabi-Yau fourfolds, it's much harder. My student Yinan Wang and I some years ago had to go Monte Carlo and found that the numbers were just running away. And then we found that actually if we do a simple-minded Monte Carlo where we limit ourselves to a subspace where we don't pass through any technical codimension 2 4-6 points, which give us E8s and things, we already got over 10 to the 50 bases statistically. Jim Halverson and Cody Long had a nice work where they, also Ben's son, I think. Sorry, I lost the third author there. They had a nice piece of work where they looked at an explicit construction using a tree sort of construction of various Calabi-Yaus, and they found 10 to the 750 distinct geometric bases for elliptic Calabi-Yau fourfolds. And then we did sort of a one-way Monte Carlo with Yinan, where if you include codimension 2, 4, 6 points, we got on the order of 10 to the 1,600, just different geometries. This is not flux vacua, this is distinct geometries. So there's a very large number of Calabi-Yau fourfolds, even at the level of geometries. An interesting point, which I'll come back to, is that essentially all of the bases, both bases that are surfaces and threefolds, support these things I mentioned, the geometrically non-Higgsable gauge groups, which has some interesting physics consequences. I'll just mention that this point up here, and analogous to the one I mentioned in my answer to your question, Emil, about the generic elliptic fibration over F12, the one with the biggest H31 has an H31 of 300,000, and that'll play an interesting role in my comments later on the standard model. Okay.
And are these
line of this whole first
distinct topological manifolds? These are distinct topological manifolds, or are some of these just different, like, points in some connected space?
I believe that these, okay, so one of the things that distinguishes these is that there are flop phases on a toric base. And I think when you look at elliptic fibrations over those will actually be topologically distinct manifolds, not just different flop phases. There's a little bit of a subtlety there, which I think requires further thought and understanding.
Sorry,
but for the most part, these really are separate geometries.
Doesn't a flop change the Betty numbers? I mean, a flop it changes the topology of a manifold.
Just changes the intersection form.
This is a flop in the toric in the base. It does not change the Betty numbers.
But it also
you have some piece of the triangulation looks like that, and you undo this, and you do that.
Well,
so it doesn't change H11 or H2.
But does it change the intersection form, as Emil said? I mean,
it does change the intersection form, yes.
So therefore, the manifolds are topologically distinct, right? I mean, intersection form is a homotopy or a homeomorphism invariant.
Yes. Okay. There are certain Calabi-Yaus which fit in common families, which are related by flops. So technically, they're topologically distinct, but they have closely related physics, and you can travel from one to the other by going, passing through.
Yes, and in fact, there are even conjectures that all Calabi-Yau defolds are in one such family. But
I don't think that's true, because there are definitely Calabi-Yau defolds with different H11 and with different Hodge numbers, and the transitions.
No, but you can do different birational transformations, not just flops.
Oh, yeah. Right? Actually, here all of these things we're looking at are birationally related, but I'm just saying that there's a more there are general birational transformations, and every single Calabi-Yau I'm talking about here is related by birational transformation, because we can always blow up and down to get to any base, and in fact, that's proven for threefolds, and I'm not sure what the answer is for fourfolds.
I think it's proven for elliptic fourfolds, but not for general fourfolds.
That they're all connected by birational
transformations, the elliptic ones.
Well, we should talk more about that. I don't know that statement. I know it in threefolds. I've wondered it for fourfolds. I think there are fourfolds which are elliptic fibrations over non-rational bases. Like let's push that offline or to the end.
Sure.
I think there's good questions there. So all these things are topologically distinct at some level, but there are some that we might want to group more closely together in terms of the physics, because the Hodge numbers don't change. It might be something you could get to with a fairly gentle transition where you don't drastically change the set of fields. Okay. Let me now jump to the second thing, which is, okay, now we have a big picture of the space of F-theory compactifications. What's typical? So the question is, if we look at a random one of these things, what kinds of gauge groups do we get? And if we fix the gauge group, what kind of matter do we get? So the first and primary point is that most of the bases force us to have some of these geometrically non-Higgsable gauge groups. Again, this is where some 7 branes nucleate on loci because there's a negative normal bundle. And so to have a supersymmetric vacuum, we have to have some gauge group. This is true both in 6D and 4D, but the presence of fluxes and a superpotential makes it more subtle in 4D. So basically, a typical vacuum has some different clusters of gauge group factors, which may have some matter. So for instance, we might have an SU3 cross SU2 with some matter living at the intersection locus. But these different clusters will only interact with one another through gravity and scalars. So this provides a very natural setting for dark matter. In other words, if we have one cluster which contains the standard model, F-theory generically will give you a dozen or so other non-Higgsable clusters, geometrically non-Higgsable clusters, which are very natural dark matter candidates. And there's a whole fascinating story we could talk about there. Certain gauge group factors arise as these generic factors that are forced by the geometry. So for instance, in 4D, we can get these gauge group factors here at SU2, SU3, SO7, SO8, and the exceptionals. But note that we can't get SU5. So again, the idea here is that on different branches of the moduli space, these gauge group factors are forced on you as part of the supersymmetric vacuum. Of course, if you break supersymmetry, you can break these gauge factors, but without breaking supersymmetry, you can't. There are also products of two factors that include matter, and it's perhaps interesting to note that SU3 cross SU2 is one of the only 5 two-factor products which appears in 4D non-Higgsable structures. And we'll come back to that later when we talk about standard model. Okay, so how practical gauge groups? Let's look back at this. As I mentioned, there's one great big moduli space for 6-dimensional supergravity and its characterization through F-theory. And this is actually related to the point you made, Clay, which is all of these branches are connected precisely because of these birational transformations that take us from one base to another. So basically, all the bases are blow-ups of the Hirzebruchs, and we can get from one to the other by blowing up and then blowing down. And then we can go anywhere on a branch by tuning the Weierstrass model. And all of this is on a flat moduli space. So we have this big moduli space of hundreds of thousands of connected branches. And you may ask, where in that big moduli space do you not have non-Higgsable gauge groups? And I don't know if you can see them. There are like 7 or 8 orange points here, which are the Del Pezzo surfaces. And those are the only places in this whole moduli space where the Del Pezzo surface is your B2 base, where you don't have a non-Higgsable gauge group. As soon as you get up to the Hirzebruch surface F3, you have a -3 curve and you get an SU3. So basically, as you blow up points on the base, you generally get curves of negative self-intersection, which force gauge groups. So a typical gauge group will be something like E8 to some high power times F4 to a power, maybe some G2 cross SU2 factors. In 4D, it's a similar story. If we look at the results of our Monte Carlo through this huge space, we just get a bunch of factors like that in every vacuum. So that's the first big lesson for physics, is that the typical vacuum has lots of gauge group factors. So now how about matter? So there's another interesting story which we can talk about, which is if you choose a gauge group, which may not be automatic, it may be actually a tuned gauge group, then there's a very natural sense in which we can identify certain representations of that group, which are what we can term generic matter. So we can do this in a very specific way in the 6D story. One of the reasons I keep focusing on 6D is because everything's mathematically very clear and well understood there. So in 6D, if we fix a gauge group, like say SU5, then in general, the space will have various branches of different dimensions. And the branch of the greatest dimension will have the most typical matter types on it. So just to distinguish this concept from what we were talking about non-Higgsable gauge groups, on the right here, we have a picture of part of the moduli space, where in the bulk of the moduli space in green, we have a non-Higgsable SU3 gauge group. And then on a special subloci, we refine that to SO8. So there, a non-generic gauge group lies on a subspace of the moduli space, which has the generic gauge group. In the matter context, if we fix, say, SU6, the generic branch will be the branch of the largest dimension. It will have the antisymmetric, the fundamental, and the adjoint. But there are also exceptional or exotic representations, like the triple antisymmetric representation of SU6. And there are branches that contain matter in that representation. And those are distinct branches, but you can reach them, as we studied with Laura Anderson, James Gray, and Nikhil Raghuram, by going through matter transitions that change the amount of matter without changing the gauge group. So these are kind of two different geometrical pictures of how generic and non-generic play together. So just a couple of quick examples. For U1, the generic matter types are charge 1 and 2. Anything else is non-generic. For SUN, fundamental, antisymmetric, and adjoint are generic. There's no antisymmetric for SU2, and the antisymmetric is the same as the anti-fundamental for SU3. So for those, we just have the fundamental and the adjoint. So in those cases, in fact, in many cases, in all the simplest cases, the number of generic matter fields is the same as the number of anomaly constraints. And so in some sense, if you fix the anomaly coefficients, there's a unique solution for generic matter. This idea of generic matter seems very robust. If we look in F-theory, generic matter is associated with the simplest singularity types. to get other kinds of matter, you really have to stand on your head and do more exotic things with singularities. Okay. An interesting observation, which I'll come back to towards the end, is that if we just take the so-called standard model gauge group, 3 cross SU2 cross U1, the matter content of the standard model is not generic in this context. The generic matter for that gauge group has nothing which is charged under all 3 gauge factors. In fact, if you take this gauge group, it's quite hard to get in F theory the proper matter of the standard model. On the other hand, if you take the gauge group to be SU3 cross SU2 cross U1 mod Z6, then the standard model matter, along with several exotic representations, is actually totally generic. So this gives, I think, a hint that the latter is the proper gauge group if F theory is telling us anything that has anything to do with how our world works. And we'll come back to that. So for a given G, the generic matter is typical and anything else is sort of fine-tuned. So for instance, for SUN, the 2-index symmetric representation, or for SU2, the 3-index symmetric representation, are exotic matter representations that can be realized in F theory, but they require exotic singularities. Basically, you need the place supporting the gauge group to have a self-intersection, or this is for the SUN with 2-index symmetric. For the 3-index symmetric of SU2, this needs to cross itself twice, or triple crossing.
Wadi, can I ask about the U1 in the standard model in F theory? What is its origin?
Yeah, I'm going to come to that. I have a whole slide where that'll be relevant. Can we just talk about it then?
Yep.
Or was the question more relevant now? Because I want to talk about that in 15 minutes.
That's fine. Yep.
Okay, great. Okay, so then the third sort of big question I want to address a little bit is this question of what is possible in string theory and F theory versus what's possible in a consistent low energy theory that we couple to quantum gravity. You know, there's this, you know, people, I think when the landscape came along, people started to worry that basically anything goes in string theory. You can dial anything you want, so you don't have to worry about it. So we know that's not true. And essentially this question about the sort of landscape versus swampland is something which has driven string theory since the very early days when Emil and David Gross and Jeff Harvey and Ryan Rome identified the heterotic string. If we go back to 1984, Green and Schwartz showed that if we look at a 10-dimensional n equals 1 supergravity theory, it looks like there's 2 type 2 supergravity theories, and then it looked like there were only 4 theories that looked consistent with anomaly cancellation. SO32, which was known to be a string theory. So this V is the space of known string vacua, and this G is the space of apparently consistent string theories. And the swampland, as dubbed by Kummer and Vafa, is the set of theories that we think are consistent, but we don't know how to get it in string theory. So in 1984, the swampland looked like this. We had E8 cross E8, U1 to the 496, and E8 times U1 to the 248. And then the string quartet, Emil and collaborators came along and showed that actually E8 cross E8 is a string theory. So that was great. And then some years back with Alan Adams and Oliver DeWolf, we showed that actually these other 2 theories are inconsistent. So in 10 dimensions, there really is no swampland, at least at the level of discrete data for a 10-dimensional n equals 1 supergravity theory. So part of what I'm trying to address with this next part of the talk is trying to look for a similar story in 6 dimensions and 4 dimensions. So there's a couple of reasons you want to do this. One is, if we can identify strong constraints from string theory on what kinds of theories we get, for instance, that match with the standard model, then it may give us very concrete predictions for what kind of physics has to come along with the standard model. And even more might be if, as in 10 dimensions, we could prove in 6 dimensions, 4 dimensions, and maybe even 4 dimensions without supersymmetry, that you only are allowed to have a low energy theory that's coupled to quantum gravity if it's one of the ones that come from string theory, then in some sense we will have proven that string theory is the only consistent theory of quantum gravity. Now we're far from that, but this is one of the things we can kind of aim at with this picture. So let me just say a few things about.
Wadi, can I throw a little shade on that? I mean, in the end, in 10 dimensions, the input from string theory is nothing, right? In the end, all of those theories that you mentioned are ruled out just by purely low energy anomaly cancellations, and it's ignorant as to the UV completion. That you know, the UV completion doesn't actually It's
Right.
nice
So
that
what,
string
what I'm
theory
saying is, if you
completes
can
them,
carry
but
that program, I mean, I totally agree with what you said, but it might be that in fact there is no other consistent quantization of gravity other than the ones that come from string theory. So that the more you probe, I mean, here again, I was careful to say at the level of discrete data, so gauge group and matter, if we could do that in 6 dimensions with supersymmetry, for instance, and in 4 dimensions with supersymmetry, you might say, well, then string theory doesn't play a role because we've found quantum consistency conditions, not necessarily low energy. They might involve things like looking at, I mean, for instance, there was an alternative way of proving that these two theories are inconsistent, which Kim, Gary Hsu, and Kumran Vafa showed. If you look at the world volume of a string in these theories, then you can't have these two theories here. You get an inconsistency. So
yeah, I mean, that's also a
this
low
is
energy
a
quantum
way
field
in which
theory
you
kind of
can learn.
consistency.
Right. Right. So, but the point is, if you can identify consistency conditions that rule out everything that's not coming from string theory, then you will have shown that string theory is the only consistent theory of quantum gravity. Now, there are things like higher order terms in the Lagrangian, but one might in principle be able to show that those are also uniquely determined. Right?
Yes,
I mean,
but I guess I'm saying that if you show that these are the only discrete allowed possibilities, then it doesn't yet tell you much about whether it's they're coming from string theory or from some other theory of quantum gravity. I mean, I don't really believe that they're coming from some other theory of quantum
well,
gravity.
but if you can also prove, right, but if you can also prove that all other
string theory makes a huge number of predictions beyond just the low energy gauge group is E8 times E8 or SO32, et cetera, et
absolutely,
cetera.
absolutely. I'm saying you would have to go to the point where you could prove that in fact the low energy effective action to all orders and all the excitations were uniquely determined to be consistent with the one that comes from string theory. So it's, as I say, it's a long way away, but it's something which at least I think is a very useful guide in helping us to look at questions that help us learn about how these things fit together.
But is your vision is your vision for the future about the swampland program something like what is modeled in the 10-dimensional situation? Because if that's true, then it means that, you know, maybe we would get lucky and work extremely hard at the level of low energy, mostly low energy consistency conditions and rule out everything based on that.
Yeah, so I think we're very far from that. I think that's an interesting vision, but what I'm going to do now is I'm going to run through like a dozen things that we don't understand very well about the swampland in 6D and mostly in 6D. And it's kind of motivated by these considerations, but I don't think that, I think it's more interesting to look at these individual things related to some of the current swampland conjectures and also related to the very concrete context of 6D supergravity, where I think we can really put teeth on these and make them very concrete and specific without making vague conjectures. So let me go ahead and do that, and maybe you can chime back in if you think that it's real, you know, there's more to be said about that, okay? So let me first of all go over some simple theories where there isn't a swampland. So if we simplify things a bit, we say, okay, let's take away the tensor multiplets, which are an antisymmetric field that appears in 6 dimensions. Look at theories with no tensors and generic matter. Then there is actually, at the level of discrete data, a very close match between F theory and 6D supergravity. But even there are some minor subtleties and some edge cases we don't fully understand. For instance, if we look at the gauge group being U1, generic matter is Q equals 1 and 2. We can solve the anomaly equations and we get a finite set of solutions. Here we have a certain number of charge 1 and a certain number of charge 2. And all these are realized in the Morrison-Park models. There's one slight subtlety, which is it looks like there's an anomaly-free theory with 108 massless charge 2s and no massless charge 1s. But it turns out that that theory actually is secretly 108 massless charge 1s. You might imagine that there are theories with massive charge 1s and massless charge 2s, but that doesn't seem to happen. And I'm going to come back to that in a little bit in a more broad comment. SU2 is a similar story. We have a simple classification of the anomaly-free theories with SU2 gauge group and no tensors. There's 12 of them. 9 of them are exactly realized in F theory. 3 of them have some subtleties. One of them automatically becomes an SU2 mod Z2. That's related to this business of the charge 2 here, because this becomes an SO3 gauge group. And 2 of them automatically pick up an extra SU2 for reasons we don't understand. So there are already places in the swampland in this very simple case where we don't know how to rule out a theory with SU2, anomaly coefficient B equals 10, but the only thing we get in F theory has an extra times SU2 in it, mod Z2. So already here, there are some kind of interesting swampland things. So to get back to your question, Clay, to me, actually, right now, these kinds of questions are more pressing because there we really have identified theories which we can't rule out, but which don't come from F theory. They're pretty special, and can we find some way of either ruling them out or finding a new string theory that gives them to us?
But these examples that you're talking about, I mean, how do you know that you can't get them from F theory by tuning? I mean, you're looking in the list of generic structures, but you can do a lot with.
So we can completely classify theories with an SU2 gauge group, at least under the assumption that you have a unique factorization domain for the ring of functions on the divisor, and those theories are not included in there. So it would have to be something very exotic. It is possible that it's there, but it's not just a straightforward tuning.
Got it.
So in a paper with Dave Morrison, we analyzed the general SUN tuning, assuming a UFD condition. And a non-UFD tends to give it, as I'll mention in a minute. If you do non-UFD tunings, you can get exotic matter, and that's how we get things like the SU2 with 4 symmetric the SU2 with, we can get an SU2 with triple symmetric matter by an exotic tuning involving a non-UFD structure. There are things that look consistent. I'm sort of moving on in the swampland. There are slightly more exotic matter representations like SU2 with 4 symmetrics. And, I think, Clay, you've thought about the SU4 with the box representation, which look consistent from low energy, but we don't know how to get from F theory. So those are more things that are kind of in the swampland. There are some conditions which are true in F theory, which also seem to be related true statements in supergravity. So, for instance, with Seiberg, we showed that the string charge lattice is unimodular. Some nice work of Samuel Monnier and Greg Moore, where they showed that the anomaly coefficient A has to be a characteristic vector, which matches with what we get in F theory. So there are these substantial constraints that come from F theory that are matched by constraints in the low energy theory. Further conditions, again, I mentioned this work of Kim Xu and Vafa. They were also able to rule out certain infinite classes of theories at large numbers of tensor multiplets. And Lee and Weigand, using similar string worldsheet methodology, were able to limit the number of U1 factors when t is greater than 0 to less than 20. So there are some constraints that can be determined from low energy type constraints, but there's still a gap between those and the things we can get from F theory. And this is, I think, just an interesting place to look. Whether or not you're pursuing the perhaps impossible dream of proving that string theory is correct by proving everything else is inconsistent, there are lots of very specific theories which look consistent, but we can't get from string theory. And so if we can either rule them in as a string theory vacuum or rule them out as inconsistent, we will have learned a lot. I'll just briefly mention exotic U1 matter. For non-abelian gauge groups, the set of exotic things is fairly finite. If we go to U1, we understand it much less, just like we understand Mordell-Weil much less. So for instance, with Andrew Turner, a current student who's going to be at UPenn next year, we found an infinite family of theories where you have 54 charge Q, 54 charge R, and 54 charge Q plus R fields. And that gives us an infinite family of anomaly-free solutions. But we know that only a finite number of them can come from F theory. We don't know what the largest U1 charge you can get in F theory is, but it must be finite. So the biggest explicit construction was Nikhil Raghuram up to Q equals 4. There are standard F theory constructions which apparently go up to Q equals 6. And I'm sorry, Paul, you had also done something up to Q equals 6. You want to say something about what you did up to Q equals 6?
We also get somehow Q equals 6 to be somehow the highest one, but it's an indirect argument. So via an indirect argument, we tried to show that a Z6 discrete symmetry is the highest you can engineer, and that would require a charge 6 guy. So from the Higgsing, because every discrete can be unhiggsed. But this was the argument. It's very indirect. But
good. Yeah. So there's some indications that maybe 6 is the right number to get up to, but then with Nikhil, we have this indirect construction that gets up to 21. So we really don't understand how big the charge can be. The biggest one must be finite because we know there are a finite number of different elliptic Calabi-Yaus and therefore the finite number of possible U1 charges, but there's no obvious bound. So finally, let me mention an upcoming paper with Dave Morrison, which is more related to these kind of swampland conjectures, One of the things that has been around in the field for many years, it was essentially what underlay Polchinski's identification of D-branes, and then was articulated by Banks and Seiberg and recently proven by Harlow and Oguri in the context of ADS-CFT, is the idea that if we have a theory with a given group symmetry, then there should be states in the theory that live in all possible charges of that symmetry. And so in particular, if we take a 6D supergravity with a gauge group G, the charge completeness hypothesis there states that there will be states in the theory with all possible charges in the charge lattice. So in this paper with Dave Morrison, we proved that from the point of view of F theory, but we also find a stronger condition, which is related to this funny U1 model with charge 2 that I mentioned. And that is, many theories in F theory, in fact most, satisfy a condition which I'll call massless charge sufficiency, which is the condition that the lattice generated by the massless states is already the full charge lattice of the theory. So in this paper, which will hopefully come out maybe even as soon as next week, we prove charge completeness for all the 6D F theory models where G is a connected Lie group, but we can't prove it for discrete factors. And we can prove it for the 7-brane part of the 4D theory from F theory. This condition of massless charge sufficiency, we analyze a huge range of cases, and we find that whenever this condition minus A dot B is greater than 0 is satisfied, the massless charge sufficiency condition is satisfied. And the exceptions are very special situations, such as the non-Higgsable gauge groups that simply have no matter, where there are massive states with charges, but no massless states with those charges. Okay, I think that's about what I wanted to say about the swampland. I think I have about 10 minutes to just say a little bit briefly about how we get the standard model in F theory, and this is related actually to some of the most recent work I've been involved in. So we have this big picture now of the landscape of 4D and 6D F theory solutions, and we can ask, where in all this crazy geometry does the standard model live? So roughly speaking, we can kind of break the possibilities up into 2 columns and 2 rows based on 2 different binary choices. One binary choice is, do we tune the gauge group, or do we assume that it's coming from one of these non-Higgsable, automatically forced negative normal bundle structures in the geometry? That's the choice of which row we're on. The second choice is, do we assume that there's a gut, a unified theory which is bigger, which then gets broken, or do we assume that we just have the SU3 cross SU2 cross U1, or at least the algebra of that gauge group? And so depending on which row you choose and which column you choose, there's a whole different class of constructions. And I actually want to walk through each of those 4 classes with one slide and just talk about where we are in understanding those. So much of the work on F theory standard model constructions was the work on F theory guts that was motivated originally and initially pioneered in the work of Donaghy and Weinhold and Beasley, Heckman, and Vafa. Beautiful review of this by Timo Weigand. And I won't do justice to all this work. There are hundreds, if not thousands, of papers on this. It's been explored very extensively. But just to say how this fits into this big picture, the SU5 requires substantial tuning in the Weierstrass model, for one thing. And the other thing is that most of the bases can't support a tuned SU5. If I go back to that picture of where all these Calabi-Yaus are, move this. Most of those places, the only place you can get an SU5 is sort of over here at small h11, because over here, there's too many non-Higgsable gauge groups. They kind of fill up the structure so that if you tried to put in an SU5, it would cross an E8 or something like that and cause a singularity that's too bad, and you couldn't get a good standard model construction. This is a well-studied approach. It's very interesting, but it requires fine-tuning and a very special base. Next, let's talk about the standard model tuned through tuning a gauge group. This has been the focus of quite a bit of recent activity. If you try to tune the gauge group without the Z6, as I mentioned earlier, the matter is very exotic for the standard model. And there's actually no construction known in F theory of an actual SU2 cross SU3 cross U1 without the Z6 quotient that has standard model matter in it. And I think it will be very hard to find such a thing. It will involve all kinds of exotic matter, Q equals 4, U1 matter coupled to charge, things that are charged under an SU3 and SU2.
How do you detect the Z6 quotient in F theory? How do you detect the Z6 quotient?
Good. You can do it by looking at the discrete structure of, there's a couple ways of thinking about it, but part of it has to do with the discrete structure of the Mordell-Weil group. that by looking at the sections, you can see it. And that is related to this proof that Dave and I give that you have charge completeness. In proving that, we use Poincare duality, just briefly. So the idea is that divisors that support gauge groups and curves which support matter in a threefold are Poincare dual. And therefore, because Poincare duality, after some appropriate projections, tells you that there's a dual pairing between the divisors supporting gauge groups and the curves supporting matter, you know that every weight in the weight lattice has to be realized for a given gauge factor. So whether there's a Z6 or not is related to whether those curves exist. And so it's related to the divisor structure. Basically, when you add curves, you're removing divisors, and vice versa when you maintain that Poincare duality. Does that make sense?
It does. I guess I'm a bit
okay,
unclear
so now,
about whether the U1 that you're talking about is global U1, and if so, how that Z6, how the argument that you gave would detect the fact that the Z6 also acts on the U1.
If there is a Z, good. Actually, I'm sorry. You're absolutely right. Let me draw back a second on what I said. The structure when the Z6 acts on a product of a non-abelian group and an abelian group is more subtle. What I said a minute ago is relevant if we have SU2 mod Z2, not in this case. In this case, you see it. It's related to the way the U1 appears. There's something called the Shioda Map, which you can sort of, again, view it in terms of this language of the charge lattice, and it's tied into this Poincare duality story I was describing with Dave. In this case, what happens is you get a kind of a diagonal tilting so that you get, if your SU2 generators here and your U1 generators here, you'll get charges that live like that at points that are off that lattice or not. And that will depend on whether you have the Z6 or not. So you can see it by looking at the dual divisors and at the divisors supporting the gauge group factors, including the Mort-Helvez, and the dual curves supporting the matter. I'm running a little short on time, so let me talk more at the end. So there's been a lot of work recently on getting the standard model in F-theory. A lot of this actually came originally from this nice work of Clevers, Mayorga, Pena, Ullman, Paragua, and Reuter, where they basically classified all the possible toric fibers for an elliptic fibration in F-theory. And they noticed that one of them automatically gives you an SU3 cross SU2 cross U1 structure. And then some further work, Lin and Svetich and Grimm and collaborators showed that there's actually a Z6 in that particular SU3 cross SU2 cross U1. And so in recent years, various folks, these folks here and these folks here have been looking at 3-generation models, and there's this paper of the quadrillion standard model constructions where they use this fiber construction to construct a very large number of standard model-like 3-generation constructions. So along these lines, with Andrew Turner, we've been looking at what I might call a universal SU3 cross SU2 mod Z6 F-theory construction, where we're able to actually basically identify the most general model that has that gauge group with generic matter. And so in a recent paper with Nikhil Raghuram, we sort of identified this indirectly with Andrew, and then we found the Weierstrass model in a recent paper. This actually has 2 branches. It's got sort of a branch 1, which has extra kinds of exotic matter, and a branch 2, which is exactly the F11 construction. So first of all, it shows that that F11 construction, which on the face of it seems like a very special toric construction, it's actually just, it's one branch of what is essentially the unique way of getting SU3 cross SU2 cross U1 mod Z6 in F-theory without tuning some exotic matter. In general, it has this additional branch, which has exotic matter. And in an upcoming paper with Patrick Jefferson, we analyze fluxes on those things and chiral matter and confirm the sort of lack of a swampland there in the sense that there are 3 independent types of generations that could come from fluxes, and they all do. Okay, so there's a whole interesting story there. This is a different way of getting the standard model out of F-theory. Like SU5, it requires tuning. It requires less tuning than SU5, but also a substantial amount. It's also only possible on small H11 bases. In particular, the thing that they used in this quadrillion constructions, everything had to have a certain divisor class minus K, which actually means that this only works on weak Fano surfaces, which are the analogs, or weak Fano threefolds, which are the analogs of the Del Pezzo surfaces I was mentioning earlier, which are like those orange dots in the big space of blue. It's a very small set of bases, you know, like 4,000 out of 10 to the 500 that support this kind of construction. But nonetheless, it's a very interesting construction that gives us a lot of the structure we might want. I'll briefly mention Sav. Do I have 5 more minutes maybe?
Yeah, please go ahead.
Okay, great. I think I'll be done in 5. So another approach which we can take, which hasn't been explored that extensively, is to assume that just at least the SU3 cross SU2 comes directly from a non-Higgsable factor. We know, we found in this work and then identified in a broader context and some further work with Dave Morrison, that SU3 cross SU2 can be a geometrically non-Higgsable structure in 4-dimensional F-theory models. This happens in a much wider range of bases than the ones where you have to tune everything from scratch, because this can be one of the non-Higgsable structures, which is part of that geometry. So it goes further out in the H11 axis. The non-abelian structure of the standard model matter is very natural in this framework, but getting the U1, and I think, Clay, you were asking about this earlier, and now I'll come back to your question. The U1 is tricky. There's 2 ways to do it. You can get it in a non-Higgsable fashion, which is difficult, but possible. We've identified some cases where you get non-Higgsable U1 factors. Yinan Wang wrote a nice paper where he did a fairly general analysis of those. They're very rare, and you have to really tune the base to get them. Otherwise, you have to tune the U1 by hand, and then there's some subtleties as to how it plays with the SU3 cross SU2. I think these are interesting questions and they need more study, but that's about all I have to say about that. Finally, let me mention one more approach, which is, and what I think is actually the most likely place we will find this eventually, which is to find the standard model through the flux breaking of a bigger non-Higgsable group. In other words, SU5, you can only get on special bases with a lot of fine tuning. All these bases, most of them, have all kinds of non-Higgsable E6s, E7s, and E8s. So if we use one of those E6, E7, or E8 factors and break it by a flux, then we have lots of places to get something that looks like the standard model. So naively, this vacuum up here at the corner of the elliptic Calabi-Yau fourfold picture appears to have the most flux vacua. We found that that has something like 10 to the 273,000 flux vacua. But the divisor, the matter surfaces here are Hirzebruch surfaces, which, according to an argument of Beasley, Heckman, and Vafa, will have vanishing Yukawas. So it's not obvious that we could get a realistic standard model in this set of things with the most flux vacua. Some interesting suggestions by Tian and Wang that maybe looking at superconformal matter for the E8 might help resolve that. That I think is an interesting direction. Another interesting possibility is there's another base out here, which was covered in a recent paper by Yinan, which has the largest H1 one rather than the largest H3 one. It doesn't have as many flux vacua, but like those things we talked about earlier, there's lots of flops in the base. So it may be that when you combine the allowed flops in the base with the fluxes, you might get lots of multiplicity. So we could be actually living anywhere in sort of this part or here if you just go by the number of vacua, by some raw, naive counting. And so then the question is, okay, if you look at these things which appear naively to dominate the landscape, what is the structure of a standard model that comes from breaking a non-Higgsable E6 or E7 or E8, and can we get close to the standard model in that context? I think it's a really interesting scenario. I think it's the one that involves the least fine tuning of all these things, and we should study it more. We're doing some work with Andrew and Patrick Jefferson right now where we're pursuing that a bit. But okay, I'm pretty much out of time, so let me conclude. First of all, I think we really have a good global picture of the space of elliptic Calabi-Yau threefolds. Most of the known Calabi-Yau threefolds are elliptic, and it seems like there's a similar story for fourfolds. Most F-theory vacua have multiple clusters of geometrically non-Higgsable gauge factors, which gives us a very natural scenario for dark matter. There's a fairly close match between F-theory and what we can get in supergravity with known constraints, at least for non-abelian gauge groups, but there's still an infinite swampland when we consider arbitrary U1 charges. Again, I think it's nice that the anomaly allowed generic SU3 cross SU2 cross U1 mod Z6 matter is realized both in 6D and 4D, so that there's not like a big swampland there. We can get all the things that look consistent from anomalies. The question is just to understand the structure of those theories better. And that ties into the final message, which is there's lots of ways of getting the standard model in F-theory. The best studied and best understood approaches seem to require quite a bit of fine tuning, at least from a naive counting point of view, both from the point of view of how many bases there are and where you are in that big space of bases and how much you have to tune the Weierstrass model once you're on a certain base. So I think looking at the cases which look more generic is a very natural direction to try to find something which matches observable physics, but which is as generic and natural and typical in the string theory landscape as possible. All right, I'll stop there. Thanks very much.
That was a fascinating talk, and we have time for questions. I have some questions.
Can I ask a question about the last point? So can you quantify what you mean by substantial fine tuning? So if you have, 10 to the whatever, 100,000 vacua that you've identified, 10 to the minus, how many of them have this structure?
Okay, so let's just talk about flux. Let's not even go into fluxes because that can be even more confusing, but let's just talk about the bases. There's this big picture of the set of, let me go back to red just a second. There's this big picture of all these different Calabi-Yau fourfolds, elliptic Calabi-Yau fourfolds, right? The construction that was used in the quadrillion standard models paper, which is beautiful construction based on the work that Paul and others did looking at this F11 fiber, that specific construction only works in the weak Fano bases, which are a subset of perhaps 4,000 of the 10 to the 3,000 distinct base geometries in this picture. I haven't obviously plotted all 10 to the 3,000 points. I've just taken a subset that people have actually constructed. But so that's a very quantitative measure. The second quantitative measure is once you go to those bases, that for either the SU5 gut models or for the tuned Calabi-Yau, you need to tune quite a few moduli. On the order of hundreds or thousands of moduli need to be tuned. Now, naively, that makes this look incredibly unlikely. There's a big thing I have not brought into this discussion, and that is that there are fluxes and a superpotential. And we don't really understand that well enough to know to what extent the superpotential that arises from generic fluxes forces us to certain loci in the base, in the set of bases. It is quite possible that if you're out here, there's a superpotential that sort of forces you somewhere back in there, or that, that there are other dynamics that push you away from there. At a naive counting level, however, I would say that both in terms of the number of bases, which is the point I'm making here, and I'll go up a little bit, and in terms of in terms of the number of Weierstrass moduli that need to be tuned. So there was a nice paper by Brown and Watari, which quantified the number of moduli in the Weierstrass model that need to be tuned to get the SU5. And it's order of hundreds or thousands of moduli that you need to tune to get the SU5. Now, again, that may be forced on you in a natural way when you include fluxes, but we haven't seen that calculated yet. So until you find a mechanism that forces you there, it looks like fine tuning, right? It may not be. It may be that there's a natural dynamics that forces you there. But those are the two things I'm referring to here as substantial fine tuning. First, the choice of a special base, which takes you away from these bases that are dominated by big non-Higgsable clusters. And second, the number of Weierstrass moduli to tune. Now, on the other hand, if we look at this last set that I mentioned, where you just take, something with a lot of flux vacua, there are E6s, E7s, and E8s all over the place. And there's no statistical pressure that I know of that keeps those from being broken down to the standard model. You throw in a bunch of fluxes, they could easily break down to the SU3 cross SU2 cross U1. So this scenario on this last slide, to me, seems actually absent fine tuning. It's just we don't understand it as well. Does that, Emil, address your question?
Yeah, I think so.
Yeah, sorry about the dog in the background.
I think Gary has a comment.
Yeah.
Hi, Wati.
Hi.
Hi, nice.
Hi, Gary.
It's a very clear summary of the state of the art. I just have a quick comment about Clay's earlier comment about the swampland. So it's true that an anomaly inflow argument is a low energy argument, but whether you have a string probe in the first place hinges on the completeness hypothesis. So you can imagine a crazy theory where there's a two form, but then there's no strings that couple to it. Then in which case there's no clear, there's nothing clearly wrong with the models. But I agree that in the 10-dimensional case, the situation is less clear because there are other arguments like the one that you and Alan and Oliver had, which doesn't require the string probes.
Yeah, that's a great point. Thanks, Gary. You're right that a lot of those arguments do require assuming completeness, and we haven't yet got a non-ADS proof of completeness hypothesis.
That's right.
Yeah. So, but I think tying all those things together, it you know, putting pressure on all these things, I think, is a very interesting part of the current research effort.
Right. So you can take the completeness as a fundamental properties of any quantum theory of gravity, just like we take holography. So if you take it as a built-in assumption, then it distinguishes the good theories from the bad ones.
Well, in some cases, right? Not in all yet.
Yeah. Okay. Thank you.
Sure. Yeah. Thanks, Gary.
So I also have a question. Thanks for the nice talk.
Sure.
So we have actually considered only the Calabi-Yau spaces that were so that had this elliptic vibration, right?
Yes, for F theory. So that's. Let me just go up to the top. Well, please finish your question, but I'll go somewhere else. Yeah.
Okay. So is there any constraint that we should be considering only such elliptic vibration, like Calabi-Yau spaces with elliptic vibration? Because if at all we consider something without elliptic vibration, we might get some gauge groups which we were not able to get in F theory. Right?
Good. So if we are using the methodology of F theory, then that presupposes the elliptic vibration structure in the sense that the elliptic fiber in F theory is not really part of the compactification space. I'm just going back to this first picture. If we take, for instance, type 2b string theory, and we compactify it on P2, that's not a Calabi-Yau space even. But we then have a Weierstrass model over that P2, which is associated with the generic elliptic vibration X over P2. But this whole framework of F theory only works when we have that elliptic fiber. And in some sense, what's happening is that fiber, the modular parameter of that fiber is really a proxy for type 2b axiodilaton. It's got the axion and the dilaton in it. So F theory, as described here, we can't really compactify on a non-elliptic Calabi-Yau, a non-elliptic space. We can do string theory in general, like type 2b on a non-Calabi-Yau. Absolutely. Right. And you know, Sav and others have looked at, you know, for instance, weakening the Calabi-Yau condition in various ways, or looking at, you know, non-Kähler spaces. But that's slightly different from what we're doing here in F theory. I think a lot of these will have F theory duals. Some of them won't.
Okay.
So it certainly is interesting to look at non-Calabi-Yau, non-elliptic Calabi-Yaus when you're doing other compactifications besides F theory. I don't know how to think about it in the F theory context if it's not elliptic.
I see. Okay. So if we start with some theory like M theory, will we be getting some U1 gauge group that we were not able to, you know, it was tough with F theory?
So in 6D, there's very little that you can get in 6D. There's a couple of, there's a whole, there are various discrete things you can get, like the frozen states that Clay and others have looked at, which are in slightly different sets of theories from what I'm describing here. So I should give the caveat that there are slightly distinct, like in the CHL string, for instance, gives sets of theories which cannot be described in F theory. And so it is certainly possible that there are other whole large sets of theories which we can't get through F theory. In 6D, we come pretty close for typical theories to getting everything that we know how to get from F theory, and with the exception of some of these, like the frozen phase things where you get some more exotic structures. So it's certainly interesting to pursue, you know, other frameworks and other structures. One other comment in response to your question. One thing that you might want to loosen about the elliptic vibration structure is the existence of a section, which is what makes it elliptic, as opposed to a genus 1 vibration just by tori. I didn't really emphasize that here, but there's a section, a special point chosen in each fiber to make it elliptic, because the elliptic curve has an addition law. If we take a genus 1 vibration, again, it's not technically the same kind of F theory compactification. There's a very beautiful story where we can relate genus 1 vibrations of M theory to elliptic vibrations of F theory, which has to do with discrete gauge groups in the theory. So you can get discrete gauge groups with constructions related to non-elliptic but genus 1 fibered spaces, although I would still technically think of them as elliptic vibrations in the F theory language. We could get into further discussion about that. But hopefully that gives you some answer to your question.
Yeah, great. Thank you.
Good thing.
I have a question that maybe is fine for now. Is there any a priori reason, other than making a list of examples, to expect that most Calabi-Yaus would be elliptic?
Yes.
Like even any intuition about that?
Yeah, depending on how many minutes I have to answer that question. I think this is a great question. I didn't put it in my talk, but I'm gonna share a, don't have it. If you could just hang on one second. Let me just give you a 3-minute answer to that question. Okay, I'm going to share a different screen. Okay, so this is a couple of slides on that, which I didn't include in this talk. But so you're asking, why is it likely that a Calabi-Yau threefold has elliptic or genus 1 fiber, right? So there's a theorem by Oguiso and Wilson that a Calabi-Yau threefold is genus 1 or elliptically fibered if and only if there's a divisor that satisfies d cubed equals 0, d squared not equal to 0. If d squared is equal to 0, it's just like K3 fibered. D squared not equal to 0, and d dot c is greater than or equal to 0 for all algebraic curves C, okay? So you can ask, let's imagine we just have a random triple intersection form. How likely is it that this is going to be satisfied, okay? And there are two possible obstructions. One possible obstruction is there might not be a solution to d cubed equals 0 over the integers. In other words, you might choose an intersection form so that you just can't solve that over the integers. The second possible obstruction is there might be a solution to d cubed equals 0, but it might not satisfy this cone condition. Okay? So let me just quickly consider each of those. Sorry. Okay, so the number theoretic obstructions. Here's an example of a cubic form in 4 variables that has no solution over the integers. And you can see that it has no solution over the integers by basically looking at the parity of the various things. If x is odd and everything else is even, then this thing is obviously odd, and therefore it can't be 0. If y is odd and everything else is even, for the same reason, this can't be 0. Let's say x and y, let's say z is odd, but x and y are even, then everything's divisible by 4 except 2z cubed, and then it also can't satisfy the condition. So this is just a simple example of something that has no solutions. Mordell in 1937 identified homogeneous degree d polynomials in d squared variables that have an obstruction of this kind. And it was conjectured that d squared is the maximum number of variables with an obstruction. It was proven for d equals 1 and 2. There's a counterexample for d equals 4. There's a quartic in 17 variables with an obstruction. Heath Brown in 1983 proved that every non-singular cubic in more than 10 variables with rational coefficients has a non-trivial rational 0. And it was proven for a general cubic in 16 variables. So the upshot of this is there can't be a number theoretic obstruction to the existence of an elliptic fiber when h11, or to this d cubed equals 0, when h11 is bigger than 15. Okay, so when h11 is bigger, there has to be a solution, at least at the number theory level. And then we can ask about cone obstructions, and I won't go through the details, but basically if we just assume we have a random triple intersection number, the probability that there's no fiber, that there's nothing in the right cone is 1/2 to the h11. So when h11 is big, there's no chance. Now, this is a heuristic argument. It depends on a Kähler cone, which is like a generalized, and that's not necessarily true. And there's actually some nice work by Cody Long and Liam and Mike Stillman looking at small Kähler cones when you go out to large h11. So there are questions, there are ways in which you might evade that, but just naively, the answer to your question is, if you have a general 3 form, you just expect there to be a d cubed that satisfies 0 in the right cone, so that you might expect that it's elliptically fibered. So I think it's a great question, which is why I wanted to take a minute to address it. Is that it? Does that give you?
Yeah, I mean, yeah, it's something to think about. Thanks.
Yeah.
But Wadi, one quick comment. But the landscape you're looking at is still, in some sense, geometric, right? I mean,
yes.
I mean, the base is still like large volume and has a geometric interpretation, which would not cover stuff that you would know from, I don't know, asymmetric orbifolds or funky. I don't
Yeah,
know.
so this is a great question. I mean, Sav, didn't you have a paper showing that some non-geometric stuff has a F-theory dual?
Yeah, yeah. A lot of the non-geometric heterotic stuff has a geometric F-theory dual. And it seems sort of, at least heuristically, that at least adding non-geometric fluxes wasn't enlarging the space enormously. Wasn't giving us something that was really new. On the other hand, here, if you went to small volume, it would be hard to know because you would need a different framework to understand what's going on.
Yeah, my problem with a lot of these things is when you get to non-geometric stuff, you're sort of forced into this highly non-perturbative regime where somehow F-theory has some magic to it, which gives you control over this big non-perturbative moduli space because of holomorphicity. And that's the only tool I know of that I really trust to give any insight into what's going on non-perturbatively in these things. So I think it's a great question, but I think what Sav said is maybe evidence that it's not obvious that there's a big set of things we aren't getting at. Certainly in 6D, I don't think there is a big set of things we're missing.
Right. Right.
I sort of have two related questions.
Sure.
If you start looking at heterotic on a threefold and taking the bundle into account, so the quintic was an example where there wasn't an obvious F-theory dual.
Right.
Is there any reason to think there could be very large families on the heterotic side that are, comparable in size to the F-theory landscape that are just missed entirely?
So my sense is no, but I'm not really confident in that answer. So the reason I say that is because, again, of this observation that most Calabi-Yaus are elliptic. So if we take heterotic on a random Calabi-Yau, it'll be elliptic. And once we have heterotic on an elliptic Calabi-Yau, that's dual to F-theory on something with the same base, but with a P1 fibration over it in the base. So the base is a P1 fibration over something else. And so we've actually, I've done quite a bit of work with Laura Anderson and others sort of looking at the heterotic F-theory duality. And it's kind of what we used in this matter transition story is really digging into how these exotic matter transitions happen both on the F-theory and heterotic side. And it seems like a lot of, I don't think we understand heterotic any better than we do F-theory in many of these regimes. And in fact, I think F-theory can give us, in some cases, more new information about heterotic than the other way around in terms of the questions about what kinds of bundles exist, right? So one of the issues that comes up on the heterotic side is what kind of bundle can you have? And there are these limited classes of bundle constructions like the monad construction and the spectral surface construction and various things. And those only give you limited classes of things. And on the F-theory side, you can match the topological numbers up and identify large classes of things on the F-theory side that seem to correspond to bundles that nobody knows how to construct on the heterotic side. So first of all, on the geometry level, where I think if most Calabi-Yaus are elliptic, most of them should have something on the F-theory side. And then in terms of the bundle side, where I think we know how to get more of what corresponds to the bundle topology on the heterotic side than we do in the heterotic dual side. I don't think I would say I haven't seen any sign of huge classes that we don't know on the F-theory side. But there are certainly things like heterotic on the quintic that we don't know how to get there. Does that sort of address your question?
Yeah, yeah. The other question I had is the enormous number of flux vacua that you're finding in that massive case. Almost all those flux solutions are not supersymmetric, right? I mean, they all have some W naught that is typically non-zero.
Yeah, I think that's true. I don't understand the flux vacua of these things as well as I would like. I think that's true. But I think the standard lore would say that that's true.
Yeah, yeah. So I don't have any. So I think most of them are not going to be actual critical points, like semi-classical critical points. But the number of supersymmetric ones is probably very small. It's probably not adding much to the geometric degeneracy that you're already seeing.
That's a really good question. I'm not sure what the answer to that is in terms of how many supersymmetric vacua there are.
It's an over-constrained system in that case, and you just generically don't expect any solutions. So if you find one or two, that would be that's already hard.
Yeah, I think that really starting to understand the flux vacua of these things in a bit more detail than people have would be a great, and understanding how that fits into this global picture would be a really interesting set of questions to pursue. And I keep wanting to pursue that, but I have been doing easier things.
Well, I think the landscape you're seeing is probably the real landscape.
It feels like it. I mean, I feel like we're getting some glimpse of this big space, and you know, yeah. So whatever we can figure out about it, I think may have some real lessons for us. One thing that gives me a lot of optimism about this picture is the way in which things that we figure out in 6 dimensions, which on the face of it looks very special, are still true in 4 dimensions. Like the structure of these non-Higgsable gauge groups, which are true in 6 dimensions, is still just very similar in 4 dimensions. And the fact that we get these different clusters, the structure of the space of Calabi-Yau manifolds, it sort of implies that some of this is not totally a feature of the large amount of supersymmetry.
Yeah. Yeah.
Yeah. So I think it's all fun and interesting. Very good questions.
Okay. Just follow maybe with one quick comment.
Sure.
On the thing before, just a quick comment on this, especially on this heterotic F theory duality overlap. So there's just one curious case where you have something in the heterotic where you actually don't know what to do in the F theory, and this is the heterotic string on orbifolds. And so there you could, for example, take your even in 60. You can take an orbifold and use the standard embedding. For some reason, the standard embedding is more complicated to get in F theory. But even for that orbifolds, what you get at matter, for example, when you take, well, in 60, you would get an E7 times SU2. And the funky thing is that you have bifundamental matter under those. So you have 56,2. And in F theory, that would immediately give you a superconformal matter. That should be not allowed, but it seems to be allowed in the heterotic string, in the perturbative heterotic string.
Yeah, I think this is a great question. I've actually, we've probably discussed this, I banged my head against this a bit, and I didn't put that case in this talk because I'm still not quite sure what to make of it. It's an interesting case where, you know, I'm not completely convinced that the heterotic side is not missing some superconformal symmetry that people might actually be there. You know, the other option is that somehow the superconformal symmetry is, the 4-6 point goes away and it's a smooth thing on the F theory side, which requires, I don't know, I guess the you know, speculation was T-brains, right? But I don't know. I think that's a great, yeah, Paul, that's one of the cutting edge questions, which I think we will learn a lot when somebody can answer that question.
Indeed, yeah. No, yeah, it lets me not sleep at night.
Is there upper bound for the U1 charge from a heterotic? For example, in 6D?
It's a good question. I should know the answer. I don't know the answer. I don't think it's above 21. I don't know. Paul, do you happen to know the answer to
that? In 8D, you're saying? 60. In 60. Yeah, I think this comes also to this statement, I think, that that Timo did, right? So that the number of U1s should be lower than 20, as far as I know.
No, I mean,
you were looking at charges, yeah. So I think, as Paul says, the work that Timo and company did indicates that everything sort of comes from the E8. So one way to understand it is what's the biggest charge of a U1 that comes from an E8? And I don't happen to know that. I think I've even looked at that once and figured it out, but I don't remember what the number is off the top of my head.
Okay, thanks.
It's a good question.
Very good. Are there any additional questions? All right, let's thank Wadi again for a great talk. As I'm unmuted, I will actually clap.
Thank you, Wadi. Great talk.
It was a great talk.
Yeah, well, thanks a lot for having me. It was a lot of fun, and thanks for the great questions.
No, it was very good. I'm going to stop the recording.